physics. So this is the plan of what I will discuss. So since I know that you are a bit sleepy because of the dinner yesterday, so I decided to highlight my presentation with some movie slides. And so let me start with the Flavour Window, which I think it's nice because this gives this picture gives a pictorial view of what we are trying to do in flavor physics. Really trying, we are not there where the action occurs at high energy, but we try to reconstruct what happens with sophisticated, machines, place it on a specific special window, which is the flavor window. So, I guess I don't need to motivate why we need to go beyond the standard model. I think we all agree that we need to go beyond the standard model. We don't know which is the scale in new physics, so we have to search for physics beyond the standard model, and we have to do that with a broad spectrum perspective, given the lack of new physics signals so far. And from that point of view, flavor physics is it's quite interesting, and has a twofold role. On the one hand, I think we really would like to understand which are the symmetries and the symmetry breaking pattern beyond, that clearly come from physics beyond the standard model that determine the observed pattern of quark and lepton masses that we observe. And so certainly this is a subject of flavor physics, actually probably is the most interesting aspect of flavor physics. And then we can use flavor physics really as an observatory to look for physics BSM, okay, looking at possible deviation in specific low energy observable. So let me just spend one more slide on this motivational issue. So the idea that we have in mind that there is some high-scale, possibly flavor symmetric theory where there is some flavor dynamics that determine this strange pattern of quark and lepton masses that you observe. Clearly, this pattern of masses, to me at least, doesn't seem to be accidental. Okay, it could be accidental, but it's more natural to explain it in terms of some symmetry. And so there should be some dynamics that determine that. And this dynamics is mediated down in the standard model only via the Higgs sector. So the Higgs is the mediator of the flavor changing dynamics. And how this mediation occurs, we don't know. But certainly, one of the really big questions is to understand eventually which is this flavor dynamics. The second, more practical question is to understand if there is some other intermediate layer, okay, between this high-scale theory, maybe gut theory or flavor theory, and something that lies in between, let's say, the electroweak theory and low energy. So if there is this intermediate layer, of course, this layer could fill the breaking of the flavor symmetry in a slightly different way. If this is the case, then we will see some clear pattern of deviation from the standard model in flavor observable. So these are really the two independent questions. Which is the dynamics that determine flavor, and eventually if there is something else that mediate flavor breaking in a different way than the standard quark and lepton Yukawa coupling. So I will come to this more fundamental question at the end of my talk, and now I'll concentrate on this one. So this first question is the one that we address really with the precision measurement in the quark sector and the lepton sector. And so this is, for instance, was already illustrated very well in the previous two talks. And as you know, if we just try to interpret this very precise agreement between the various measurements in terms of possible bound on new physics, so if we just take an effective theory approach and we include a higher dimensional operator, and we try to fit the scale in new physics, we find this very heavy, this remarkable bound on the scale in new physics, which are certainly much above the scale probed in accelerator. However, one should not overemphasize this bound on the scale. And so let me just give you an example, a very simple example to show why we should not overestimate this strong limit on new physics. So let's take, for instance, mu to E gamma, a very simple process on which we have the theory prediction is perfect, so we don't have actually in the standard model we expect essentially 0. So of course, this process, we have a bound coming from meg of the level 10 to minus 13. Of course, if there is some new physics that mediate this transition, we can put a particle here, some coupling, for instance, the mu and Yukawa coupling and theta 1, 2, the mixing in the lepton sector coming from neutrinos. If we put this coupling, we find the bound on the scale of this mediator at the level of 200 TeV, so a really remarkable bound. And you see here, this coupling are very natural. But of course, it's an assumption. I can put also still reasonable couplings here, but different ones. So I put also the electron Yukawa coupling, and I put mixing coming from the quark sector. And here, you see that if I put this more suppressed coupling, the bound I get it's much weaker. Okay, it's 10 GeV. So if you want, this is in a sense the weakness of flavor physics that we cannot determine if maybe new physics is very heavy or maybe has a highly non-trivial flavor breaking pattern. But these also highlight the potential of flavor physics that really can explore scenario with very small coupling or very large masses, which certainly cannot be explored by the high-PT experiment. So really, it's the complementarity of flavor physics that is very important. And so on general terms, we have these two options which are still open. And what is clear that there is still a wide and possibly interesting region of new physics parameter space that we have and must explore with flavor physics, with both in masses and coupling. So we have to really push forward this field even with more new sophisticated instruments, okay, as was discussed before. So let me now be more concrete and let's discuss a few observables. So let's start with the usual suspects, which are the standard CP analytic observable, VUB, and so on. So, and I will discuss the sensitivity of this observable in a specific concrete framework, which is supersymmetry. And so let me say, first of all, that supersymmetry remains, I think, a very interesting candidate for DSM physics. First of all, because it's a weakly coupled theory, so we expect small deviation from the standard model there on general grounds. It predicts a light Higgs, and actually 125 Higgs is really well in the ballpark of the SUSY prediction. And of course, there's also nice visual like dark matter unification, as was already emphasized by Marcella yesterday. Of course, we need some tuning in the Higgs mass in the MSSM. Now, this is clear, but I think we should not, again, overemphasize. I mean, do we really care if fine-tuning is 1% or even 1 per mil? That, of course, would be better no fine-tuning at all, but this is still not dramatic. And actually, the theory in the SUSY concept that alleviate this fine-tuning problem are those where we allow a flavor non-trivial spectrum. It is a spectrum where, for instance, we decouple the third generation of squarks, which is more important to tame the fine-tuning problem, from the other squark, which can be very heavy. Okay, so this is what people sometimes call natural SUSY. I don't call it natural SUSY because I think it's still not extremely natural, but I call it split family SUSY because I think the key point is really that we split the family, and this is very important for flavor physics. Okay, this is something that can be motivated in specific flavor models. And so LSE experiment and the high-PT experiment have started to directly explore this framework with high-PT searches. But flavor physics here plays a really important role because of this non-trivial flavor structure where there is a relatively light third generation of squarks and leptons. And so in this case, because of the exchange of these squarks, we can expect visible, let's say 5–20% effect in the usual suspects, so epsilon k or the phase of BB bar mixing, and also in some clean rare decays. So there has been a lot of discussion about this in the literature. Let me just pick now one really specific example, which is a concrete realization of this framework with a specific flavor symmetry, which is U2 cube, which actually is a very protective flavor symmetry. So if you buy this idea of MSSM with a protective flavor symmetry, you expect small effect, controllable effect in value of observable. So this is analysis by Barbieri and collaborators, where they have taken into account all the present bound from CMS and Atlas on the masses of squarks and leptons, okay, and gluinos and so on, and then they compute this observable, for instance, the ratio of delta MB sub D over delta MB sub B over the standard model, epsilon k, and so on. And this is, you see, there is still a wide region of possible deviation up to even 60%, okay, in this observable if you just take into account high-PT data. Then, of course, we have to put in the direct flavor, if you want, the indirect constraint from flavor observable or the direct constraint on this observable from flavor. And so, of course, the parameter space is reduced, but still you have a sizable room for deviation. And so you see, this is a nice way to illustrate the interplay in a specific framework between high-PT and flavor observable. And of course, I mean, if one day we will be able to reduce the error at the level of few percent, of course, this will be really imply a strict correlation between flavor observable and eventually, I mean, charged Higgs mass and so in this specific framework. And let me stress, as was already discussed by Tom, that actually there is really room for 20% deviation in the mixing, okay? In the mixing process, like actually Tom was speaking about the phase of BB bar mixing. I would say, for instance, in this framework, the most interesting case is new physics in epsilon k. I mean, we can really have new physics. You see here is the standard model CKM fit without epsilon k. So this red band, sorry, this green band, black curve is the epsilon k constant, which I remove from the fit. And so this is the preferred solution, okay, without epsilon k. So you see that there is some tension, which so could be well accommodated by a 20% or 10% new physics effect in epsilon k. Of course, when you put everything together, you don't see that. But so this just tell us that there is room for some 20% deviation epsilon k, and note that in the case of supersymmetry with this generic but constrained flavor structure, we expect a positive contribution to epsilon k, which is exactly what we slightly see from data. And so how can we detect these in the future? Well, we have to improve our theoretical control on epsilon k, and the theoretical control on epsilon k is controlled basically by the other ingredient here in this fit, and especially VUB is the leading theoretical uncertainty, the leading parametric uncertainty. So the possible improvement on VUB from B2 tau nu or from B2 pi nu from BEL2 will be a very important ingredient in this game to reduce error. And of course, also the determination of gamma from LSAB is very important. So I think this is a very interesting field on which we have to improve, okay, the precision to reach the few percent level. Okay, another typical example is B mu. Okay, B mu was already highlighted. It's very clean in the standard model coming from these electroweak penguin diagrams. And again, in this specific framework can be modified by stop contribution or heavy Higgs amplitude. There's been a significant progress here on the theoretical side to reduce the theoretical uncertainty, and you see now that the present error is at the level of 7%, which is remarkable for anadronic decay. And the error will go down in the future because, again, here is the dominant uncertainty is the parametric uncertainty, mainly from the lattice form factor, which is lattice is steadily progressing here, and also, again, from the indirect constant from the CKM fits. And here, this is the present experimental situation. So, of course, at this stage, there is perfect compatibility between theoretical prediction and data, but I think we are only at the beginning. We really have to enter in the few percent precision era. And you see here, again, an example in these constrained models. Actually, this is an even more constrained model, is the constrained MSSM, where you see the possible prediction of this R mu is the ratio between BS mu in the model compared to the standard model. So 1 is the standard model, and of course there is a wide region where we don't see any deviation, but there are regions, I mean, at lower masses, so this is the mass of the heavy Higgs, where we can have deviation at the level of 30%, which are still compatible with present data and can be eventually detected in the future. Okay, so this is what I want to say about the standard clean modes. And let's now go to a bit more sophisticated observable, which have been started to be discussed especially by LSAB. So these are the B2K star LL. So here my reference movie is Star Wars, because of the charming penguin saga, which I think is quite interesting. It's an old saga, as you remember, in Flavour of Physics. So here I don't repeat the various analysis of the experimental result, which was very nicely discussed by Johannes. So let me concentrate on the anomalies, or if you want, on the tension. And before doing that, let me make a few general considerations. Okay, so similarly, I mean, similar to BLLL, also B2K star LL is a very clean, very sensitive probe of physics BSM, because it's a received contribution from electroweak amplitude, and so there is no three-level contribution within the standard model, and there is a strong suppression because of the CKM hierarchy. However, the key point to be addressed and is the difference between BLL and B2K star LL, that in the case of the B2K star LL, because of this extra hadron indefinite state, QCD effects are much more important, and so the theoretical control is more difficult. So to control this process, to predict it from theory, we have to undertake 3 steps. The first step is the construction of a local effective Hamiltonian at the electroweak scale. This was, again, nicely discussed by Johannes this morning. And this is the easy step. Okay, so we integrate out the heavy degrees of freedom, so for instance, the W and the Z, and we construct a series of local operators, Q9, Q10, and so on, at the electroweak scale. If there is new physics, this new physics will modify this coefficient of the operator, okay? So, and at this level, there is no difference among the various B2SLL transitions, so no difference between B2LL or B2K star LL. Then what we have to do next is the second step is to evolve this effective Hamiltonian from the high scale down to the scale where the process occurs, so the B mass scale. This is, again, a step that we can do in perturbation theory at the level of effective operator. And here we start to see some difference. And the difference comes because, okay, we have not only these nice electroweak penguins, so operator of the type B2S LL, but we also generate at the high scale simply 4-quark operator like B2S charm anti-charm. And this B2S charm anti-charm, we think they are less sensitive to new physics because they are generated at the 3 level. But when we go down, they can mix, okay, and they can generate an effective B2S LL amplitude, because, for instance, if I put here a photon, okay, this effect is large. Actually, it's really large in the case of Q9, so the the case where we have the lepton pair in a vector state. While it's really negligible when we have Q10, so the lepton state in the axial configuration, because in that case only the Z contribution can appear here, and this is highly suppressed. So here you see the big difference between B2LL, which is sensitive, so B2LL is sensitive only to Q10, while B2K star LL is sensitive both to Q10 and Q9 is the one that is polluted, if you want, by this QCD effect. And finally, there is the third step, the most difficult one, that finally, okay, still at this level, we are at the partonic level, then we have to evaluate the matrix element, so really the matrix element between the initial hadron and the final hadron configuration, okay, so the matrix element of our 4-quark or 4-fermion operator. And here really come the non-perturbability effect, which are very dangerous, and particularly in the case of B2K star, we have the CC bar threshold, which really disturb us because it's a difficult non-perturbability problem. Also here, there is an important difference between the exclusive and inclusive decays, because in the case of the inclusive decays, we can use the operator product expansion, the 1/MB expansion, so we have much more systematic control of the uncertainty, while in the exclusive mode, it's more difficult. So now, let's now come to the anomalies or the tension. So the first tension is this famous P5 distribution. So P5 is a ratio of different angular coefficient, which is actually constructed in order to minimize the sensitivity to the form factor. And so here, as was already discussed, there is a 3.7 sigma discrepancy with the prediction, okay, of the standard model. And there is also a second anomaly which fits well together with this, that is the overall smallness of the 4-branch ratio. 4-branch ratio, when I mean the branch ratio of B2 hadron and mu, and there are the 4 different hadrons, so K star 0 or plus, and K plus or K0, okay? And so, in favor of new physics, there is this fact that if we can really reduce the tension with data in both cases, so the branch ratio and this P5, with a unique fit, okay, of modified Wilson coefficient. So mainly is this Q9 operator, actually Q9 and Q9 prime, which are really the photon penguin operators. So if we modify their coefficient, so if we introduce new physics that modify this coefficient, you see we find this is one of the results of this combined fit. It's been done by various groups. So this is the standard model, and the best fit solution is 2 sigma away from the standard model. So first of all, it's 2 sigma, so it's not striking, but it's interesting. And what is also interesting is that the scale is heavy. So it's, I mean, the corresponding effective scale, yes, it's 10 TeV. So can be a reasonable new physics contribution. Now, against new physics, however, is the fact that, first of all, you see the discrepancy is mainly in 1 bin in Q square, so one should not take it too serious, and also it's a bin in Q square which is close to the, here there is a hole because there is the J side, okay, so it's a dangerous region. And, and also there are some groups that claim maybe here the uncertainty, the theoretical uncertainty has to be enlarged. Now, this is a long debate. For instance, there was a nice presentation in the parallel session where it has been confirmed that actually that I think if we take into account all the correlation, the theoretical error is really not too large on this bin, at least according to some reasonable model. This is still a kind of debated issue. My main worry, okay, this is a personal opinion, is that new physics only in these photon penguins is a bit suspicious, because really the photon penguins are, as I discussed, those which are more sensitive to possible on this effect. It would have been much nicer, okay, if one could have found some evidence also in, say, Q10, and this is not the case. So this is why I'm a bit skeptical. Now, even more interesting, now there are other tensions emerging, and this is an interesting recent work done by Zwicky and Lyon. They analyzed the high Q square spectrum in B2K mu. This is the channel on which we have the highest statistics. So here we can really afford to make a fine binning in Q square in the high Q square region. You see these points are the LSEB points, while this curve is the curve obtained using the factorization approach on how to evaluate the CC bar scattering effect, and then using E plus E minus 2 CC bar data to really take into account what should be the dominant non-perturbative effect. And you see that there is a big discrepancy. For instance, one see a peak here, actually one that should have not been seen according to this theoretical prediction. So what this tells us? Well, I think, first of all, this I think is an interesting study because it is really an attempt to try to take into account the leading non-perturbative effect, but seems to show a clear failure of the factorization approach, which actually is the leading hypothesis on which we compute the form factor. And so this cannot be explained with new physics in B2SLL operator because it's really a non-local effect in Q square. So maybe, for instance, Zwicky claims it's new physics in B2S CC bar operators. Actually, in this case, you can have a good fit And actually, in this case, indirectly, you can also have new physics in B2SSL because of the scattering of CC bar. But I would say it's very, very contrived from the point of view of model building. The nice thing is that future data can help to clarify this picture, because first of all, we can try to have data also really in the resonance region to understand better this non-perturbative effect. So I think it would be interesting to see data also closer to the Psi1S and Psi2S region. Also, it would be nice to have a fine Q-square building also for other modes, like in particular the K-star. And finally, I mean, probably the decisive answer, if we don't understand the picture of the exclusive mode, could come from Well2 with the inclusive mode, where we think we have really much better theoretical control. And finally, last tension I want to mention is this deviation of lepton universality that was discussed by Johannes, where this is a 2.6 sigma deviation from the standard model. Here, the key feature is that the theoretical prediction is very solid. QCD cannot affect lepton universality. So from that point of view, we are safe from the theoretical prediction. So maybe this is, if it is really confirmed, could be really a clean signal, maybe of new physics in B2S EE, but certainly these do not fit in a trivial way with the previous anomaly. So maybe it's just an indication that the situation is complicated and we really need more data. So my final consideration about this mode that there are some intriguing hints in B2SL operators, in B2SL, sorry, transition, but clearly there is no a firm evidence of new physics. It could well be that experimental fluctuation plus the theory error may explain all these effects. And the good thing is, as I already pointed out, that more data, both on the exclusive and hopefully also on the exclusive mode, could help to clarify the picture. Okay, so probably I will skip now this fact about flavor physics with the Higgs boson, because as I said, the Higgs sector is really the mediator of a high scale of a possible theory that determines flavor. So from that point of view, studying the flavor violating effect with the Higgs is very interesting, but this was already nicely discussed by Andre yesterday. So this nice result on the limit on the Higgs to mu tau. So since my time is short, let me concentrate on the final part of my talk, which is coming back to the big question. That is, what determines the observed pattern of quark and lepton matrix? So this is really the key question in the sense of flavor physics. It's a difficult question. It's a question that we have there since ever, okay, since the beginning of flavor physics, and we have not a clear answer. So let me try to give you my view on that. We have two roads to address this problem. One is the standard road, the symmetric way, so really trying to find symmetry. And of course, more recently, there are new ideas. I mean, trying to use anarchy and entropic selection. So just to say that maybe the masses of the pattern of the Yukawa coupling is just determined by entropic selection, like similar to the cosmological constant. I think this works well, for instance, for the light masses, because if we change a little bit the mass of the up and down quark, we immediately end up in a non-human friendly universe. It also could be a nice argument to have anarchic neutrinos, because neutrinos do not play any role from the point of view of the entropic principle. But I would say, what about the CKM and what about the other masses? I don't find this explanation very, very convincing. And also, maybe this entropic principle could be really, or if you want, the idea of the multiverse and the entropic selection is a good idea maybe for the cosmological constant, but doesn't need to be the explanation for everything we don't understand. So I want to continue on the standard way, or the symmetric way, because clearly I think there is a natural hint from the point of view of the Yukawa coupling of a symmetric structure. Is less evident, but as you will see, could well be there also in the neutrino case. So my idea is that a large flavor symmetry with small breaking is the best way to go, and this is particularly motivated by the absence of new physics signal in flavor changing neutral current. So let me go along this line with the idea of a large flavor symmetry with small breaking. So this is what I mean by large flavor symmetry and small breaking. Well, the largest flavor symmetry we can invoke is the U, for instance, in the quark sector is U3 cube. Okay, so this is the symmetry behind the idea of minimal flavor violation. That is, we have this huge flavor symmetry in absence of Yukawa coupling, and then we break this symmetry only with the Yukawa coupling. Okay. This is nice because naturally explain why we don't see big deviation in flavor changes of currents, but there is a problem because there is no explanation of why the Yukawa are what they are. So this is the question that I want to address. There has been other attempts in this direction, for instance, to use different symmetries still relatively large, like U2 cube that I mentioned in the case of supersymmetry, which is better because, for instance, in the case of U2 cube, you explain why the top has mass while the other not. But again, this is put by hand. So the problem of this approach, especially of the approach attributing a special role to the hierarchy of the Yukawa coupling, first of all, there is a problem with the neutrinos, because as you know, in the neutrinos, we don't observe any big hierarchy. So why the neutrino is so different? Okay, why we don't see any hierarchy there if this hierarchy plays an important role? A second, actually more important drawback is the fact that this ansatz for the symmetry breaking is put in by hand. So we just buy the Yukawa from what you see from experience. So it would be nice to have a dynamical explanation. And there's been some interesting progress from that point of view by various groups. I mean, really trying to build explicit models that determine the structure of the Yukawa starting from this big flavor symmetry. So I don't have time to discuss all these recent approaches, which are interesting, so let me just concentrate on my own work on this, which I think probably highlight the most important aspect. So let's assume that the Yukawa are really dynamical fields, and we want to determine their structure from minimization, a potential which is invariant under the big flavor symmetry. So for instance, U3 to the fifth, if you really just take the largest symmetry. So this is a simple minimization problem. So we have to write down the potential. Of course, we have several options for the potential. And the nice thing is that there are some natural solutions to this problem. And this is something that was discussed long ago basically in the 60s. The generic problem that if you have a large symmetry group and you want to determine which are the most natural solution, okay, of your field that break the flavor symmetry, the initial symmetry. And the answer is that there are always some natural solutions, I mean, solutions which are independent of the specific detail of the potential. So are solutions which really remains there even if you include radiative correction and so on, because these are really solutions determined by the symmetry structure of the theory. And see, these are the solutions that preserve maximally unbroken subgroups. So this is a theorem. One can demonstrate a theorem by Michel Radicati that tells you that if you start from a large symmetry and you want to understand which is the natural symmetry breaking pattern, the natural symmetry breaking pattern is the one that preserves the maximally unbroken subgroup. So if we start from U3 to the fifth and we introduce the Yukawa or the neutrino masses as potential field that break the symmetry, we have two options, okay, which preserve large unbroken symmetry, which are the hierarchical option, so surviving chiral symmetry, and in the case of the neutrino, especially because the neutrinos break the field in a different configuration, is a Majorana mass term, the maximal symmetry is an O3 symmetry, so which imply degenerate neutrinos, okay? So first of all, we have a very simple, according to these old ideas, very simple understanding that the two natural possibilities are either hierarchy, that is what we seem to observe in the Yukawa, or degeneracy that we hopefully could observe in the neutrino case. But even more interesting, when we try to put the two things together, now in the lepton sector, the neutrino mass matrix and the Yukawa coupling in the lepton break the same U3 to the left symmetry, and so we have to consider the two breaking together, and there is a natural way to put the two things together that leads to a maximal mixing in the neutrino. So this mass matrix corresponds to degenerate neutrinos with maximal mixing, and this is one of the two possible options, okay, of maximal unbroken subgroup. So I think this is a very nice, so just one of the possible orientation of this O3 with respect to the U2 unbroken here. So again, without making any specific detail, just assuming a symmetry and assuming that this symmetry is broken, we find that a very natural configuration is that of a pi4 maximal mixing between the third generation and the last generation in the neutrino sector, which is, as you know, is what we observe. And finally, if we put in perturbation, of course, we have to perturb this solution because we want to have masses for the light generation, and we also want to have some mixing in the neutrinos. Again, naturally, just assuming that the perturbation is small, you predict that one of the angles in the neutrino is order 1, but not maximum, and the other one is small. Again, this comes for free, okay? And so, of course, this is already observed, so it's not a prediction, but the prediction of all these frameworks is that the neutrino masses have to be almost degenerate, and so from the size of perturbation that we can measure, we predict that the mass of the neutrino has to be about 0.1 electron volt. And this, as you know, has an important experimental consequence, that is, if the average mass of a neutrino is 0.1 eV, so the sum of the mass of a neutrino is about 0.3 eV, we should really be in this degenerate configuration, which implies that neutrino-less double beta decay should be very close to be observed, actually, are about neutrino-less double beta decay are about to exclude this possibility. But I think this is a very interesting possibility. I would say it's our possible nice, if we observe that, it would be a very, very nice argument against anthropic argument, at least for the flavor physics, which I think would be nice. So conclusion, I think I briefly stress that flavor changing transitions represent a unique window on BSM physics. They really can allow us to explore high masses or small couplings, which we cannot probe directly at high PT. So it's very important to continue to explore this field with more and more precision. And as I as I highlighted, the usual suspects, so epsilon k and phi s and bs and mu, everything there fits well with the standard model, but we are still at the level of 20, 30% error, unfortunately, because of the combination of theory and experimental uncertainty. And so new physics signal could well hide at the 10% level. And so in well-motivated framework, so it's essential to improve the quality, especially of the CKM fits, to eventually highlight this effect. Well, we have this interesting puzzle of B2K star LL decays, where maybe there is some hint of new physics, which would not be totally unrealistic, actually could well be there. But of course, the picture is far from being clear, and the good news is that more data can help us to clarify the situation. Finally, okay, I had no time to discuss is to tau mu, but again, it's interesting that now we can do flavor physics also using high PT probes, and especially the Higgs is a very special player in this game because, as I said, the Higgs is the mediator of flavor violating interaction in the standard model. And finally, as I outlined at the end, we should not give up on models trying to explain. So we should not give up on the theory work of trying to explain from some first principle the masses and the mixing from symmetry principle. And from that point of view, I think really putting together quark and lepton is maybe the key to go. Okay, thank you.
So we have time for a few questions. Yes, quite a few here.
Yeah, so early on in your talk, you talked about epsilon k, some weak indications of. So I would have thought this is highly correlated to the error on VCB.
You're right. I totally agree. Yes.
So is it possible that you may be taking, one may be taking a more, a smaller error rather than what it is? So can you elaborate a little bit?
No, I totally agree with you. Actually, so the prediction of epsilon, so on epsilon k, the experimental accuracy is infinite, okay? It's perfect. The theoretical prediction, okay, there is the uncertainty on the form factor, which actually we control well with lattice, and then the dominant uncertainty comes from the CKM fits. And so I highlighted there is the uncertainty coming from VUB, but as you also said, actually there is also an important uncertainty coming from VCB. So it will be very important. Actually, I really, if I don't know what to bet, but I think it's very natural to have 10% new physics epsilon k, and this could really be there, and we really have to dig precisely in this CKM fit to reduce the uncertainty on VCB and VUB, because if the central values remain what they are, and we can decrease the error, there is a 10% effect in epsilon k, which is, as you know, really the most sensitive probe of physics BSM in the flavor sector. So we absolutely need to improve the precision on VUB and VCB.
So on the B2K star LL case, so there used to be that the 4 backward asymmetry was observable that captured all the angular information, especially the 0 of the 4 backward asymmetry was a very clean observable. Is that in agreement with the predictions still, or what is?
No, that is in good agreement with the prediction. Okay, so the 0 of the 4 backward asymmetry, it's well, the uncertainty is still relatively large, but we don't see any significant deviation. Right. These other observable P prime, maybe I think I have, let's see if I have, yeah, so I have a slide on what's P prime. Okay, P5 prime. P5 prime is a specific combination which is sensitive to one of these other angular correlation. You don't see that in the standard 4 backward asymmetry because you integrate on the angle, and so you wash out the effect. And this is what is nice because it's a ratio, okay, of 2 different coefficients. So here there is a ratio form factor similarly to the 4 backward asymmetry, but it's a different ratio, which, okay, it's, in a sense is more sensitive to the value of Q9 and Q9 prime. Because it's larger, so it's, in a sense, it's easy experimentally to measure it.
But would you say that the theoretical uncertainty in this observable is comparable to the position of the 0 in the 4 backward symmetry, or this is larger theoretical uncertainty?
Well, that's a tough question. Well, my personal opinion is that the control on the 0 to the 4 backward symmetry is better. Okay, there really, I think we have a better control. Here, especially because that is really a 0, so in a sense it's better to control, the effects are small, and so the situation is more than control. Here, the prediction is large, so if I go back, you see, indeed, not everybody fully agree on which is the theoretical control on that. Yeah, on this, you see, this is the theory prediction for this P5, especially in this bin here. I think we have even the most conservative error seems to indicate a deviation from data. Okay, so this is a fair statement. So there is something going on here. Most likely, in my opinion, it's just a fluctuation, okay, because it's one of the bin. So we have to be careful and wait what will happen. For instance, we have seen it with the isospin asymmetry between B2K plus and B2K0. There was a big deviation from data, and the theory prediction actually we were, I think, good enough not to inflate the theory error, because finally now the experimental error, the experimental result changed. So.
Gino, you referred to this 10% type of new physics in epsilon k and B sub epsilon plus or minus, and then you talk about the SUSY, the split SUSY models. So what do you expect? I mean, you can start with minimal flavor violation at high energies, do the running, get some splitting, or just put it ahead. What would you say that you would expect as information that you could get on these ideas of split family models from these sectors to tell us in the near future for model building?
Well, of course, epsilon k alone would not tell us too much. And indeed, in a sense, if you want, the virtue of epsilon k is that also is sensitive to other type of new physics. For instance, in Randall-Sundrum scenarios, with, again, the most natural observable where to see the first signal is epsilon k. This is just because epsilon k is extremely suppressed in the standard model, and so it's a very nice probe of third generation type phenomena, both of supersymmetry and non-supersymmetry. So clearly, you should see some pattern of correlation to eventually identify this phenomena. For instance, in this specific case that they discussed, there is an interest correlation between epsilon k and B2S gamma, which both should be enhanced. And actually, if you look at present data, both are enhanced, although consistently with the standard model, but they are both 1 sigma above, okay? So if you could reduce the error and really see this pattern, this already, I think, really goes into the direction not only of third generation type effect, but even of that this fits well with this flavor symmetry. So I think this is, and finally, of course, we should really observe the third generation mediator at a high PT, because I mean, if the stop, for instance, is responsible for that, you should see it at run 2. So we don't escape from that.
But it tells you something about how much this is split. So you can quantize how large this splitting could be if you do better measurement.
No, because that holds there even if you send to infinity the other masses. So that actually tells us that the score cannot be too heavy. The stop cannot be too heavy, but the others can be infinity heavy, no problem.
Okay. I think we should proceed to let us thank Gino again for this nice talk.